Okay, this video deals with binary arithmetic, and this particular slide deals with binary addition. Binary addition is very easy. There's four simple rules that I'm sure are obvious. The first one is 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1, and then 1 plus 1 equals 2, but in binary 2 is 1, 0. One additional rule that we'll need is 1 plus 1 plus 1. Of course, 1 plus 1 plus 1 is 3, but 3 in binary is 1, 1. Here are two examples of binary addition. The first one is 22. Which is the base 10 number. 22 in binary is 1, 0, 1, 1, 0. Plus 13, 13 is 0, 1, 1, 0, 1. Okay, so you just add the binary numbers just like you would decimal numbers. So 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0, but we have to carry the 1 to this place. So 1 plus 1 equals 0. Again, we generate a carry. 1 plus 1 is 0. Carry the 1. Okay, here is our result, 1, 0, 0, 0, 1, 1. And if you convert that back to binary, you'll see that it's equal to 35, which of course is the correct answer. Okay, here's another one over here. 27 plus 24 equals 51. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 0. Carry the 1. Okay, here's an instance where you have to add the 1 plus 1 plus 1, which is 3, which is a 1. Carry the 1 over to the next place. So the answer is 1, 1, 0, 0, 1, 1. And if you convert that back to decimal, you'll see that that is 51 in base 10, and of course that is the correct answer. Okay, so now we're going to move on to representing signed binary numbers, and we're going to use a system that's called the 2's complement form. Okay, so for binary positive numbers, there's really no change. You just represent the number in binary the way you've always done it. But the very important thing is that the leftmost bit, the most significant bit, must be 0. And of course that means there has to be a sufficient number of bits to represent the number. We'll talk more about that later. Okay, now, what about negative numbers? Now, negative numbers, you represent the positive number in binary. Then you do two things. The first thing is you flip the bits, and by that I mean you change the zeros to ones and the ones to zeros. Okay, you get that resulting number, and then you add 1 to that, and then when you're finished, that leftmost bit will end up to be a 1, and that indicates in the 2's complement system that the number is negative. Okay, so we've got a couple of examples here. We want to represent the number plus 14 in the 2's complement system using 5 bits. Okay, very easy. All we have to do is represent the number 14 in binary, and notice that that most significant bit here is a 0, and that's going to indicate that that number is positive. Okay, now how about the number negative 14? Again, using 5 bits. Well, we start out by representing the positive equivalent of that number, which is the same thing as we had right here. So that's plus 14. Then the 2 steps are we flip the bits. So we have a 0 converted to a 1 to a 0, 1 to a 0, 1 to a 0, and a 0 to 1. Then we take that number, that's just copied again down here, and we add 1 to it. So we have 1 plus 1 is 0, carry the 1, so that's 1, and we have 0, 0, 1. So 1, 0, 0, 1, 0, that number is negative 14. Here's another example. Represent the number negative 1 in the 2's complement system using 4 bits. Okay, so we start out by representing the positive equivalent, 0, 0, 0, 1. We flip the bits, we have 1, 1, 0, and we add 1, and that gives us 1, 1, 1, 1. 1, 1, 1, 1 is negative 1, base 10, in the 2's complement system. So this one is an easy one to recognize, regardless of how many bits you have. If it's all ones, you know that it's negative 1. Okay, now suppose you have a binary number, and it's in the 2's complement form, and I ask you what is its decimal equivalent. Okay, so the first thing you do is you look at that leftmost bit. If that leftmost bit is a 1, then that means that this number is negative, and if you want to know the decimal equivalent, then you have to take the 2's complement of that. Okay, so in this case, of course it is, and so therefore we flip these bits, and when we do that, we get 0, 1, 0, 0, 1, and then we add 1, and 1 plus 1 is 0, carry the 1, 1, 0, 1, 0. We convert that back into decimal, which is 10, but the original number was negative, so we have to assign a minus sign. So this number up here in its decimal equivalent is minus 10. And when you do this, don't forget to put that minus sign in there. Here's another example. You're given the binary number 11001. It's in the 2's complement form. What is its decimal equivalent? Okay, you look at that leftmost bit right there. It's 1. That tells you that the number is negative, and you've got to take the 2's complement. Okay, so first step is to flip the bits. When you do that, you get 0, 0, 1, 1, 0. Then you have to add 1. You get 0, 0, 1, 1, 1. Okay, this is the decimal equivalent of that is 7, and so therefore the decimal equivalent of 11001 is minus 7. When you take the 2's complement of a number, it's the same as multiplying the number by negative 1. So what's significant about that is if you take this negative 7 that we just converted right here, and we take the 2's complement of that, we get the number 7 back again. And of course, that is the same thing as taking that negative 7 and multiplying it by negative 1, and you get plus 7. Okay, so now we're going to move on to doing subtraction in binary. Now, this is actually pretty easy because we know from algebra, just giving an example here, 10 minus 5 is the same as 10 plus a minus 5. This 5 here, this second number, is called the subtrahend. So, to do subtraction in binary, we take the 2's complement of this number, the subtrahend, and then we add that to the first number, which is actually called the minuend. So when we do that, this is what we're doing. We're getting 10 plus a minus 5. Here are two examples of subtraction. So the first one is 10 minus 5, and we're using 5 bits. So this number right here, this is the number 10 expressed in binary, and this is the number 5 expressed in binary. Okay, so this number, the 5, is the subtrahend. So we have to take the 2's complement of that. Okay, so here is the 10 again. And then after we take the 2's complement of the 5, which is right here, we end up with this. So this number is really negative 5. And we're adding that to the 10. So we get 0 plus 1 is 1. 1 plus 1 is 0. Carry the 1. We have 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. And we generate a carry over here. Now this carry over here is disregarded. This bit is disregarded. It's thrown away. So we end up with 0, 0, 1, 0, 1. And of course that number is 5 in binary. And that's the correct answer. 10 minus 5 is 5. Okay, here's another one. 6 minus 8 using 5 bits. Same procedure. Here is the 6. Here is the 8. The 8 is subtrahend. We have to take the 2's complement of that. We get this. So here is the 6. This number is the negative 8. We add. We get 0, 1, 1, 1, 1. This time, there's no bit to disregard. There's no extra carry. And so this is the answer. Now, if we look at this number, we can see that the most significant bit here, this leftmost bit, is a 1. That means the number is negative. Well, if you look back at the problem, it should be negative, because 6 minus 8 is negative 2. So, if we wanted to know the decimal equivalent here, we'd have to take the 2's complement of this. And when we do that, we get 0, 0, 0, 1, 0. And that number is 2 in decimal. So, therefore, this is negative 2. And, of course, that's the correct answer. 6 minus 8 is minus 2. This is a very important formula for determining the number of bits that will be necessary to store a 2's complement number. And this is the formula right here, minus 2 to the n to 2 to the n minus 1. Now, the thing that's very important about this formula is n is the number of magnitude bits. And what that means is that's the total number of bits excluding the sign bit, and which just amounts to the total number of bits minus 1. Okay, so let's try a couple of examples. What's the range of signed numbers that can fit in 8 bits? Okay, so we use this formula, minus 2 to the 7th power, right, because there's 8 bits, that's 7 magnitude bits, to 2 to the 7 minus 1. So if you evaluate 2 to the 7th power, it comes out to be negative 128 to 127. Okay, let's try another one. Range of signed numbers to fit in 10 bits. Okay, so that would be minus 2 to the 9th to 2 to the 9th minus 1. You evaluate 2 to the 9th, it's 512. So it's minus 512 to 511. Final example, what's the largest positive number that you can fit in 16 bits? Okay, the largest positive number would be given by this formula, or I should say this up here. So that would be 2 to the 15th power minus 1. You evaluate 2 to the 15th power, that's 32,768, minus 1 is 32,767. One last example here. I have taken 4 bits and enumerated all the different combinations of ones and zeros that you can have in 4 bits. And I did this simply by counting in binary from 0 all the way up to 15 with 4 bits. Okay, now all the numbers on this side, this column right here, have their most significant bit as 0. So therefore, if these numbers are all in 2's complement form, these are all positive. So their decimal equivalent is 0, 1, 2, 3, 4, 5, 6, 7. Okay, now all the numbers in this column are negative because that most significant bit is 1. And this one you should be familiar with. This is -1. And if you convert or take the 2's complement of these others, you'll find that this is -2, -3, -4, -5, -6, -7, and we get to this one, which is -8. Now this one is kind of a special case, because if you take 1, 0, 0, 0, and you take the 2's complement of it, you're actually going to get the same number back again. You're going to get 1, 0, 0, 0 back again. Okay, now the rule for that is that you just convert that into decimal, which is 8, and you apply the negative sign because the leading bit there originally was 1. And you can see that if you have 4 bits, that using the formula from the previous slide, the range of values that you can have with 4 bits goes from -8, which is right here, to +7, which is down here.